Thank you very much. I was telling Antonio that I'm very grateful and very excited about this invitation, because many years ago, I think 2004, 2005, I started to work in the interface of quantum field theory in curved space-time with quantum information, and some years later on with quantum metrology. And I think this is the first time I am invited, well, maybe second or so, but I'm not usually invited to your community. So for me, it's very exciting, and I'm very grateful to show you what we've been doing. I actually fall in between fields, no? So because I'm not really quantum information, I'm not quantum field theory in curved space-time, and so on, because I mix things. So it's great when I manage to reach out like this. So thank you very much. So yes, I'm going to tell you about my work on quantum sensors. So this is going to include gravimeters, gravitational wave detectors, quantum clocks, but I don't use quantum mechanics like most people do. I actually use quantum field theory in curved space-time. So I'm not very, I don't know if there's a lot more going on in like sensors underpinned by quantum field theory in curved space-time. In my knowledge, not. So I think this is like a really amazing opportunity for the field of quantum field theory in curved space-time to look at possible applications. I hope you find this interesting. Okay. So I want to start by thanking everybody that has been in my group. Like I was telling Antonio, my group now has dissolved because I moved from Nottingham to Southampton, and I'm in the process of rebuilding it. So I will talk a little bit about some opportunities in my group for both postdocs and PhD students. But I want to thank all the wonderful contributions for postdocs and PhD students that have been part of my group. I'm going to show you sort of the outcome of, I don't know, like 10 years of work, including all the contributions of these really wonderful people to work with, and same collaborations in theory and also in experiment. I'm at the moment having, well, I've been for many years discussions with experimentalists, in particular with Philippe Boyer and Chris Westbrook, who were actually involved in several applications to do these experiments. So we've recently already got some funding. So we're now looking into actually doing what I'm going to talk about today, start doing it in the lab. So, well, I'll just start a bit with a motivation. So there are many fundamental questions unanswered in fundamental physics, and a lot of them are underpinned by our difficulty. I mean, finding the answers, no, is hard because we actually don't have a full theory that allows us to discuss in a consistent way quantum effects and general relativistic effects. So we do have some pieces of the puzzle, but they don't always fit in together, and there are many problems with bringing the two theories together. Of course, one of these big pieces of the puzzles would be quantum field theory in curved space-time, which allows to discuss many very interesting physical phenomena at the interplay of quantum mechanics and general relativity. But one of the main problems that we have is that we don't have instruments and experiments that allow us to go to physical scales where quantum effects and general relativistic effects occur and interplay. So these are our scales that we're coming very close to. So that is part of my talk. I want to tell you how we're now we're basically there, no, approaching these scales. But up to now, we've really had to rely on theory and on mathematics to make predictions. So I put this picture on the right, thinking about how people would talk about cosmology without the telescope. So if you just look at the sky with your own eyes and you see, you know, stars, it's very difficult to come up with a meaningful theory of cosmology. But then Galileo invented the telescope, and telescopes have developed immensely during the centuries, and now we're able to see very far into the universe and see that the universe is expanding and so on, and come up with much more meaningful theories for cosmology. And the same thing happens in the small scales. The Greek came up with the concept of the atom, but it's until you develop the instruments, the microscopes, and you start observing that you can come up with, you know, atomic physics and much better theories. So when it comes to the scales where quantum mechanics and general relativity interplay, we're worse than in the right side, because here at least we could look at the sky with our own eyes. We're completely in the dark. There's no instruments that allow us to look at some of these scales where we could expect to have new physics. So what I've done in my group for all these years is that I've tried, I'm a theoretician, but I've tried to propose experiments and design instruments that would allow us to approach these scales. So let me talk a little bit about the scales, but I think that, you know, one of the main thing missing is this interplay between theory and experiment. So we're hoping that the developments in quantum technologies that have been achieved recently, which are really outstanding, will allow us to put some of these pieces of the puzzle together. So, well, this is just a bit alluding at the scales where we expect to have quantum effects. We've always thought about going to very small scales where electrons and atoms live. And of course, the general relativistic scales are associated with a large scale starting from Earth up to the observable universe and so on. But quantum technologies have shown us that sort of these distinctions start to blur. So to give you an example, quantum technologies with satellites have in the last years developed very, very fast. And well, when I was working in my PhD, the experiments would take place at tabletop experiments. And then in, let's say, 2011, people started to do experiments with entanglement across 2 islands, for example, in the Canary Islands, 144 kilometers separation, something like that. But then a few years ago, there was MICUS. This is a satellite launched by the Chinese group together with the Vienna group, Anton Seilinger, that is purposed just for doing quantum experiments and quantum technologies in space. And they've been able to distribute entanglement across thousands of kilometers. So this idea that, of course, these are photons, which are very small systems, but the idea that quantum mechanics applied to small scales, well, we've seen that we can actually keep entanglement in very, very long range. So something that occurs at these scales is that, well, relativity kicks in, because the proper time close to Earth is different to the proper time on satellites. And we know that from GPS. GPS needs to make corrections due to the proper time with general relativity. So then it becomes interesting to ask questions of what happens to entanglement and quantum technologies like teleportation or cryptography when relativity kicks in. So to give you like an example of a good question would be, with quantum mechanics, the typical thing you would have is superposition. So a photon can be in a superposition of being, let's say, at different heights in the space-time. But because of GR, when you have mass, time can flow different at different points. So how does these two effects interplay? That you have on one hand superposition, things in 2 different places at the same time, but the time flowing at different rates in the different points in space-time? So these are very interesting questions. So this is one of my line of research that I'm not going to talk about today, is taking into account the space-time of the Earth using quantum field theory in curved space-time using the Schwarzschild metric. And then we've been able to see how the propagation of wave packets of light on the space-time of the Earth are modified due to the curvature of space-time. And then we say how this affects quantum teleportation, quantum cryptography, and we've also proposed a way on how to use it, how to use the changes on these wave packets to estimate the space-time parameters. So turning it around and say, okay, since the wave packets are modified by gravity, now we can turn around and use quantum metrology to estimate the space-time parameters of the Earth. So this is a full line of work that we have. We have several papers in this direction. And this would be also an application of quantum field theory of curved space-time into quantum technologies. It's a bit more about, correcting for errors that are not being considered in so far. And actually, like, groups that have the satellites have contacted my group and come to visit us, because sometimes they have effects that they don't understand. And then they think, okay, they might be coming up from quantum field theory and curved space-time. The usual thing is just to think about the phase shifts, the gravitational phase shifts, but actually our work has shown that the effects go beyond. Another way in which quantum technologies are reaching relativistic scales is by very massive systems. So again, when we thought about quantum experiments and so on, it was always a few atoms and so on, but a Bose-Einstein Condensate is a collection of up to, for example, with hydrogen, they've been able to condensate 10 to the 10 atoms. Typically would be rubidium 10 to the 5, 10 to the 6 atoms. That would be a typical experiment, but people have been able to condense up to, let's say, 10 to the 8 in sodium. So basically what you have, the atoms, and you cool them down, they can reach picokelvin temperatures. So these are the coldest experiments that we have. These temperatures are really like incredibly close to zero. And when you have the atoms cooled down that cold, the wave function of each atom starts, they all overlap and they create what we call a condensate. When you have the wave functions of each atom overlapping and very well in the ground state, with a bit of temperature, of course, because we can't have zero temperature, but we do go very, very cold. So one of the lines of research that I'm not going to talk about today either is with big mass, and how if you had, for example, a Bose-Einstein condensate and be able to make a superposition of the condensate, very massive one, put the atoms in two places at the same time, you might get gravitational induced collapse, which is an effect that has been proposed by Roger Penrose, and we've worked together on some new ideas on how could we see this in the lab. This doesn't use quantum field theory in curved spacetime, but this just shows that quantum technologies are starting to reach scales where you might see these effects. The most typical experiments in this direction with big mass are with molecules. So Markus Arndt in Vienna was able to put 10 to the 4 atoms in a molecule in a superposition of 2 different places. And people are now working towards doing this with silicia beads that have maybe between 10 to the 8 and 10 to the 10 atoms. Now, the one that I'm going to focus on, and my favorite one, is quantum precision. So when I told my colleagues in quantum field theory in curved spacetime that I wanted to use quantum technologies to measure time dilation and curvature of spacetime and so on, they first told me I was completely nuts, because at small scales, space-time is basically flat and that one would never see that. But I think that what these colleagues didn't have in mind is how precise quantum technologies are. And let me show you in this very nice examples, how even if the scales seem to be very small initially, the precision of quantum clocks allows you to see the curvature of space-time and time dilation. So the first experiment was done by Dave Wineland in NIST, in which he had an atomic clock. So an atomic clock is a collection of many atoms. Now, as in the condensate, like again, there are many atoms, but in this case, they're in a thermal state. They're not cooled down to the ground state, so they're like in a cloud instead of in the condensate. And each atom is a two-level system with a very well-defined frequency and acts like a clock, and then you get the time from the whole sample of your clocks in your potential. So he had one of these atomic clocks, and he measured the time dilation as he brought the clock up 33 centimeters. So this was done many years ago, and I think it was the first time people saw time dilation with atomic clocks in this way. And as I said, the first experiment was with 33 centimeters. And then later on, this started to improve. And there's been two papers coming up on last year, really impressive, in which they were now able to see time dilation with a separation in the millimeter scales. And actually now this became a very interesting question, because if you look at now a single atomic clock. Now, first it was the clock at one position compared to a higher position, but the precision of these clocks has improved so much. They're up to a 10 to the minus 18 and going beyond that. You start getting the possibility of seeing time dilation within the millimeter scales. So that means that it's now coming comparable to the size of the atomic clock. So you can see here in this picture, now you will have that the atoms in the bottom of your clock will see a proper time different from the atoms on the top. So one needs to really be now careful with atomic clocks, taking into account relativistic effects, which they weren't because they didn't have these precisions before. So if you just have the atoms being independent of each other, you wouldn't have so much of a problem, because you could use quantum field theory in curved space-time, and I'll show you a little bit more about that in clocks, to correct for it, and you take that into account. However, people in the field of atomic clocks want to entangle the clocks, because when you entangle the atoms in your sample, you get higher precisions. So now if you entangle all these atoms and the proper time is different at each height, the whole notion of clock time is lost. So that is another area of research that I have. I'm going to show you some very recent results that we did with light, but now one of the projects that we have, new projects, is trying to address this question with atoms, with the atomic clocks, using quantum field theory. Well, we want to use quantum field theory in curved spacetime. I'll tell you a bit more of that. It's not so obvious how to do that. But I think that the main thing I want to say here is that quantum technologies have extremely high precisions. So as I will show you with my work that I'm going to talk about now, you can sort of use this precision to measure things in quantum field theory in curved space-time, like, for example, particle creation due to space-time dynamics. And I'm not talking about analog gravity. I'm not talking about simulated effects. I'm talking about real space-time effects. So before I go into that, when one in quantum technologies thinks about measuring gravitational effects, usually the first thing that comes to mind is an atom interferometer. So what that is they throw around, let's say, 10 to the 5, 10 to the 6 atoms into an interferometer. In this case, they're again a cloud. They're not condensed. Usually there's some, you can condense them, but typically they wouldn't be condensed. And they're considered to be independent. They try to avoid interactions, because the interactions actually cause unwanted noises in these schemes. So they made each atom go in a superposition of 2 different spatial trajectories, and then using lasers they recombine the trajectories, and the phase difference that is picked up has information about, for example, the local gravitational field, or it could be used also for gravitational waves and other gravitational effects. The precision of this, the error in estimating, for example, the acceleration of the Earth goes like 1 over the square root of the number of measurements. So the number of measurements is the number of atoms. K is the mode number. And the most important thing here is the time of flight squared. So the bigger the interferometer, the better precision it has. And you see, it's a very simple equation, so there's not much room to change that. So I write here that it's a single particle detector because, as I said, interactions are avoided. I write here that it's local because the 2 trajectories are made to interfere at one point where you get the interference that you pick up on the phase information that contains the gravitational information. And I wrote here that this is compatible with Newtonian physics only. When people describe these experiments, they use non-relativistic quantum mechanics. And so that is compatible. You could talk about measuring gravity in a compatible way if you put Newtonian gravity. But now people in my field have become very interested in looking at things with proper time. As we saw, the clocks measure differences in proper time, so they want to use the atom interferometer using general relativistic effects. However, you can't do that. People put the proper time up and down, and then the inner products are not Lorentz invariants. The inner products are not Galilean invariant either. So although you can put it there and calculate, you're not getting a proper physical theory. So the right way to look at this would be using quantum field theory in curved space-time. And there's been some people working on that, getting some partial results. I've done some work on that too, but this is something that still needs to be done properly, and is one of the things that I'm interested in. So like I was saying, in order to get good precisions, you need to make it bigger and bigger. So my colleague, for example, that I mentioned, the experimentalist Philippe Boyer, had put an atom interferometer in a plane, and he's actually amazing because he pilots the plane himself as well as doing the experiment, and they go in free fall for a little bit to get these long times of flight. He also has an amazing experiment underground. This is like a tunnel that measures 300 meters, and he has, instead of a LIGO type laser interferometer, he has an atom interferometer, and he's planning to use this to measure a few things. Also in quantum field theory and curved spacetime, that's where we're working together. And this is from my colleague Ernst Rassel. He has a tower in Hanover that drops atoms, and they also have like this is like 20, I forgot if it's 10 or 20 meters. I think it's 20 meters fall. So they've been moving to getting things bigger and bigger and bigger to get higher precisions. But like I said, this is really constrained to the size. So if you wanted to have a miniaturized gravimeter, for example, to make it portable, with this sort of paradigm, you can't, because you're constrained by that. There's been some attempts to get miniaturization in that case by, let's say, throwing electromagnetic fields and slowing down the atoms. But as you see, the way of doing it is the same. It's interferometry in space, having each atom going in 2 different trajectories. So we've proposed a complete new way of using cold atoms as sensors to measure a number of things in gravity. And this is not underpinned by quantum mechanics, but by quantum field theory in curved spacetime. So the idea is not to have the atoms in free fall and having them in superposition in space, but instead of doing that, to trap them in a box potential. So for example, this comes from a real experiment, from an experiment made in Cambridge, in which they condensed atoms in a Bose-Einstein condensate in a box potential. You can see very nicely quasi-uniform density. So in this case, instead of neglecting excitations, interactions, you have completely the opposite thing. The atoms are colliding and they get entangled. And what they do is that they give rise to phonon modes. So these are frequency modes. They're sharp in frequency, and the atoms are completely delocalized in the potential. So I wrote here that it's interferometry in the frequency domain, because we're also going to do interferometry, but not with atoms in two places at, in a superposition of two trajectories, but we're going to take two different frequency modes and we're going to do interference with that. So I wrote here that the interferometry is non-local because at all times, all the atoms are completely delocalized in the potential and they're interacting all the time. And we use parametric amplification. The atoms collide and they give rise to nonlinearities. And these nonlinearities give rise to parametric amplification in the system. And that is something that we use because it leads to higher precisions. And like I said, this is a proposal for a sensing technology that is completely underpinned by quantum field theory in curved spacetime. So, well, the sort of let's say belief usually in quantum field theory in curved spacetime is that the effects are very small and one cannot see them in the experiment. So for example, I mean, just with what is the one, particle creation by the dynamical Casimir effect, just moving, let's say, a Bose-Einstein condensate in the lab. And if you did it with light, moving the walls in a cavity, you would create two particles in the lifetime of the sun. If you could move the sides of the cavity with, like, say, 10 to the, what is the maximum velocities that you get in CERN? I forgot, I think 10 to the 18 meters over second square could be. Well, the fastest you get, let's say if you could move mirrors that far, you would create that small excitations with light. So that's why people would think, well, we can't really do experiments because these effects are too small. So let's do analog experiments, simulations instead. But what I'm going to show you is that if you use not light, but a Bose-Einstein condensate instead, you also have a relativistic quantum field. However, in that case, the effects are much, much, much larger. And in principle, you could observe these things in the lab. So the main idea would be to put your Bose-Einstein condensate in your box. You have your frequency modes, and these are phonons. So the phonons are a massless quantum relativistic field in which the excitations don't propagate at the speed of light, like in light, but they propagate at much lower speeds, which are the speed of sound in the BECS. I'll show you some equations related to that. Antonio, can you more or less tell me with time, how much time do I have? Oh, I can't hear you.
You still have 20 minutes, I think.
Okay, I'm going to speed up a little bit because give you more of the technical stuff. So you pick some modes, then you do your interferometry sequence, which would be entangling those modes, for example, beam splitting them or squeezing them. Then comes your gravitational wave or whatever you're going to measure, and then you do the inverse transformation and you measure your modes. So using the same scheme, I'm going to show you today how you could use this to make a continuous source gravitational wave detector for high frequency gravitational waves. I'm also going to give you some of the latest results on now the clocks, but using, in that case, light, but looking at the proper time changing throughout the whole clock. And we've also have some proposals for measuring dark energy. I actually patent an idea to measure the local gravitational field, in this case using quantum field theory in curved spacetime and using frequency interferometry, not spatial interferometry. And we are also doing some applications as searches for dark matter. Now, the nice thing about this again is that because it's underpinned by quantum field theory in curved spacetime, it allows us to talk about effects that are compatible with both quantum mechanics and GR, not with the one that the atom interferometer that is really basically mostly described with non-relativistic quantum mechanics. So if one would be able to do one of these experiments. One would also be able to demonstrate, for example, particle creation in the phonons due to changes in the space-time dynamics. So the space-time dynamics, the changes could be due to a gravitational wave, but it could also be produced in the lab. For example, if you had separated from the BC, you had a bead and you oscillate that, that would create a gravitational field that's changing, that would affect the phonons in the BC. So you could also measure that. And we have a paper on that too. So this is basically how it works. You have, if you cool down all the atoms as much as you can, you would describe the wave function of the atoms in this way. So you first would have, if you had all the atoms not interacting and in the ground state, they would be described by a classical function, which is your mean field. And this obeys an equation called a Gross-Pitayevsky equation. But because the atoms collide, then you need to look at perturbations over this. And the perturbations are the density fluctuations or the phonons, or they have many names, no? The phonons, and these are your relativistic quantum field. So there are a perturbation on the mean field. We've done this in the BEC in a box, in which the density is uniform. And we've done that just for mathematical simplicity. Usually experiments with BECs are in a quadratic potential. And you could also do the analysis that I'm going to show you today. In that case, it's just more complicated, but in a box, it becomes very simple. So what you do is that, let me show you the Lagrangian. So this is the Lagrangian for your Bose-Einstein condensate. It's really beautiful because you can write it in a fully covariant way. So people in my field in Bose-Einstein condensate would usually not write it in a covariant way, because for most experiments you don't need to. But if you want to now talk about the effects on the underlying space-time on your atoms, then you can write it in a fully covariant way. And this is very nice. So this term here is just your kinetic energy of the atoms. And you can see here the underlying space-time metric. This is a correction to the trapping potential. The V is your trapping potential. This is your relativistic correction. And then this term is the interactions, the collisions between the atoms. So if you use this Lagrangian and you plug in your ansatz, which is that you have all your atoms in the ground state and just a small perturbation on this was due to the collisions of the atoms that are your phonons, then you will find that your phonons obey a Klein-Gordon equation in an effective curve metric. And this is how your effective curve metric looks like. This is the density of that, in this case is uniform. This is the effective speed of sound. So the effective speed of sound is going to depend on the collision rate of the atoms. And this is your flows. So you can make your velocity flows, the spatial part of them 0. And that would mean you have your BEC in a box and there's no flows. It's completely still in the spatial degrees of freedom. So I would say that the ocean is still. And why you do that is because you want to see if changes in the underlying space-time would create changes in your phonons, in your fields. So what analog gravity is about, or simulations of space-time is about, is changing experimentally the density of the BEC or the speed of sound by changing the collision rate, or your flows by using lasers or something like that, changing the potential in order to simulate on the left-hand side a known metric. So you could do that, for example, we have some papers proposing how you could do that to simulate gravitational waves or simulate dark energy models. And for example, Jeff Steinhauer measured an analog of Hawking radiation using velocity flows in like a waterfall potential and so on. But here we're not talking about simulating things, we're talking about having the space-time metric really change and measuring those effects. And I think this is important because if you do a simulation or an analog experiment, you cannot falsify the theory. You can make it behave in a way you want it to behave, and that is amazing. I work on that field. I also think it's very interesting and and important, and one learns a lot of things by doing that, but falsifying the theory needs a real effect. So, well, here you can see in the simplest case that I'm going to talk about is 1 + 1 dimensions, but we've done the work in 3 + 1 as well. You have here your Klein-Gordon equation. Like I said, the phonons are massless, so you don't have a mass term. And because we're putting the phonons in a box, you have a discrete spectrum, and you quantize the field in the usual way. You have a time-like killing vector field, and you distinguish your solutions to the Klein-Gordon effect in the Klein-Gordon equation for your given metric. So your metric is going to depend if you want to measure a gravitational wave or the local gravitational field, and you use the Schwarzschild metric and so on. That's where all the different applications come up. And then you quantize your field. So here you can look at the effective metric in the case that the space-time is flat. So you can see it looks very much like the flat metric, only that you have this conformal factor, but because it's a massless system, you can get rid of the conformal factor, you can ignore it. And then you have your usual flat metric, but you have the speed of sound here replacing the speed of light. So you can then quantize your phonons in your box, and you can here see the spectrum. So it looks like the spectrum of just a relativistic quantum field, but you have the speed of sound instead of the speed of light. And you then have your solutions, which are the sine functions, and you can just quantize this in the usual way. So the first application I'm going to show you is a proposal for detecting high frequency gravitational waves, which are monochromatic and persistent, long-lived. So you have here your space-time metric is your flat metric plus a small perturbation, and your perturbation is the usual gravitational wave perturbation, is quadrupolar and so on. And here you can see your effective metric that the phonons see. And again, you have a conformal factor that you can ignore. And the metric looks very much like the metric of a gravitational wave, only with the speed of sound replacing the speed of light. So basically the phonons are your relativistic quantum field, but the excitation, the propagation, it just has a different velocity of propagation. So I'm going to show you the 1 + 1 dimensional case, but again, 3 + 1 we've also studied. And so you have here the perturbation in 1 + 1 becomes very simple. So you just have this correction to your metric. And in this case, as I said, we consider it to be monochromatic. So this is the amplitude of your gravitational wave and the frequency of the gravitational wave. And what we're going to do is that we're going to take our box, we're going to change the potential in the box in a resonant way to excite two modes of your BEC that are going to be in resonance with your gravitational wave. So there was some papers criticizing our work, saying, no, this doesn't work. If you had a gravitational wave, you would never excite any phonons in a BEC. And this is because that criticism was considering that the initial state was the vacuum state. And yes, our results shows that if you started with like the vacuum state or your thermal state, the coldest you can get, you would never see anything. What we're proposing is to excite a two-mode squeeze state, which is very, very sensitive. And then what you would see is how the excitations in your phonons can move. So you get beam splitting. This is what this slide is about, or extra squeezing. And this is what you would observe. So now if you want to see, you prepare your phonons and you want to see what happens to them due to the space-time dynamics, then you calculate that using Bogoliubov transformation. So this would, for example, be my BEC in a squeeze state before my gravitational wave comes by. Then the gravitational wave, I here draw it in this way that looks like the box is moving, but well, you know how that really goes, but just to show it in this way. But what you get is a Bogoliubov transformation. So I can calculate how my modes change due to the gravitational wave using sort of in and out and the usual techniques that one uses in quantum field theory and Kerr spacetime. So we get mode mixing given by the alpha coefficients. and we get squeezing, giving usually as the beta coefficients. And then we calculated the alpha and the beta Bogoliubov coefficients for the gravitational wave that I showed you, to the monochromatic gravitational wave. So this is how the interferometric proposal goes. You cool down, you put everyone you can into the ground state, which we call the pump state. And this is usually in a coherent state. So then you change the trap and you excite a 2-mode squeeze state for 2 frequency modes that resonate with the gravitational wave. Then you use another transformation that's called a tritter, which is a 3-mode BIM splitter. So like a mode mixing in the 3 pump modes and the frequency modes. Then comes your gravitational wave, and then you do the inverse transformations. So the 2-mode squeezing operation here is giving in terms of the covariant matrix formalism, which is what we use. And this is the tritter transformation this is the symplectic transformation corresponding to these operations. And then we measure. So also there was some criticism on the first work that we did in 2014 because we were requiring high phonon numbers, so squeezing a lot of squeezed phonons, and also long lifetimes for the phonons. And this was because back in the time when we did this paper, there was nothing in the literature from experiments of how long phonons could live at these frequencies and so on. So we had to use other papers to more or less guess. But then people were worried that this was too much to ask for current experiments. So now our recent work shows that if you, this was without doing the tritter, so that if you do this interferometric sequence that I showed you in the previous slide, you can get the same precisions that we were proposing here, but now you can relax and getting much shorter phonon lifetimes and much less squeezing. So we've done a lot of work since 2014 to show that this is something that can be done in the experiment. And as I said, we're getting funding to do these things in the experiment. So we use techniques in quantum metrology. So in quantum metrology, what we do is that we have a figure of merit that is called the quantum Fisher information, which basically what it does is that you pick a good state. So this is like, if you pick the vacuum, that's what I was saying before, you won't be able to measure anything. But if you get to here something, a good state, like a squeeze state or something that is highly entangled, then that will give you a much better result. So you pick a good state, then comes your gravitational wave and modifies the state. So basically it encodes the amplitude of the gravitational wave on your initial state. So your output state will depend on the amplitude of the gravitational wave through the Bogoliubov coefficients, because it did some mode mixing and some squeezing. Now you want to compare this state with an increment, the same state, but with a different infinitesimal increment in your amplitude and your parameter, and you compare this. If this is called the fidelity, is just the overlap of the state. If this is 0, means that your input state was badly chosen for this transformation and you won't be able to estimate anything. If this is much smaller than in the measure that this is smaller than 1, it will be better and better and better in order to estimate the parameter. So basically, the more your output state changes, the better you can estimate your parameters. So this is at the heart of quantum metrology. So the error in estimating, in this case, the amplitude of the gravitational wave will be bounded by the number of measurements that you make and the quantum Fisher information, which, like I just said, basically amounts to comparing the output state. This is written here in the symplectic matrix formalism, so using the covariance matrix and so on, so it looks different, but I'm not going to go into that level of detail. So we studied this quantum Fisher information in terms of Bogoliubov coefficients many years ago in 2014. So we basically re-looked at the formulas for quantum Fisher information written down using the covariance matrix formalism and Bogoliubov coefficients. So if you wanted to make an application of quantum field theory in curved spacetime, and you have the Bogoliubov transformations of whatever you want to measure, you could plug it into our formulas and get some estimation of how well you could make a sensor for that. So we basically did that for the gravitational wave detector that I was talking about, and we found this is the error in estimating the amplitude of the gravitational wave. So before I showed you that in atom interferometry, this depended only on the mode number, the time of flight in spatial interferometry, and the number of measurements. And in this case, with frequency interferometry, it's much more complicated. This is what we get. So this is the atomic mass. This is the angle of the mode mixing that we used. This is the number of atoms in the ground state. These are the number of squeezed phonons in the squeeze state. These are parameters of the trap, the area, the length. The speed of sound depends on the scattering length, so it depends on the scattering length, on the time of integration. So because we're considering long-lived gravitational wave sources, we can integrate to, let's say, up to 3 months or a year or something like that. And this is the lifetime of the phonons. So, you know, the interferometry in space is limited by the size of the BECS. So you need it to be bigger to have bigger precisions, basically. But this is interferometry in the frequency domain. So we're not limited by the size, but we are limited by how long our modes live. So if your phonons live a long time, that is like having a bigger detector. But the nice thing about it, and that's why we made a patent of this, is that you can shrink it and you can miniaturize the system as long as you find a technique to make the phonons live a long time. Okay, so this is sensitivities that we got theoretically. This is an optimization because, as you can see, this depends on many parameters, and all the parameters are interconnecting, and you also have a lot of constraints. You need to be in the phonon regime. You need to be in the ultra cold regime. We consider weak interactions. And then you have a number of sources of noise. So you have 3 atoms collide and they create something called 3-body recombination. They form a molecule that is not trapped by your potential and you lose it. So you have a lot of sources of noise in which you start losing your atoms. And we considered all of the ones that are typical in a BEC, and this gives us our constraint. So these are some papers in which we studied decoherence sources for phonons in a BEC. And more recently, one of my master's students, I used to be in Vienna as well, so he wrote his thesis on studying how much could you squeeze the phonons in a BEC and how much could you let these frequency modes live to give you the right precision. So that is on the archive, and we're in the process of publishing some of his results. So these are basically the numbers. If you want in the questions, we could go through them, but you get sensitivities here, like for example, maybe I show it in a plot, that are in principle promising for detecting these effects. So you can see here how the sensitivities increase with higher phonon lifetimes. So these are phonon lifetimes of 0.06. In the work that we got criticized, we were looking at 10 seconds. So that's why they got a bit worried. But now we did in the new work, we're looking at times that range from, let's say, 0.05 or something like that to 0.5, so milliseconds and so on, so much shorter lifetimes. But you can see how making the phonons live longer gives you much better precisions. So here what I did is that I found some models for long-lived gravitational waves produced by glitches in neutron stars, and the characteristic amplitudes are predicted to be in this range. And I compared this with our sensitivities to see if in principle this looks promising, and I think it does. This is unfair because these are real experimental effects, and this is just our theoretical predictions, but I put it together with the plots that show you the sensitivity ranges for LIGO and LISA and the different detectors. So you can see we're not competing with atom interferometry in that sense because they are in low frequency, nor with LIGO or anything like that, because our proposal works in the high frequency range. So it would be complementary to that. So that's been something where we've been very successful recently. We've been invited by the community working in the detection of high frequency gravitational waves, because they've identified this proposal as one of the most promising for going on ranges that are not accessible with current detectors. And at these frequencies, you can expect to have not your standard sources for gravitational waves, but some exotic sources, like, for example, dark matter among them. So that's why we're focusing a bit of that. So this is a slide I stole from a talk by John March Russell, who works on ultralight dark matter models. And he was telling us how in this pink region, they were looking for dark matter in CERN, and they didn't find anything in this by single particle scattering of dark matter. And because, you know, going to a bigger accelerometer would be too expensive, people in his field has been looking at other options, and they've been studying what happens to not single particle scattering, but collective behavior. And interestingly, there are models for the collective behavior of ultralight dark matter that predicts bosonic behavior. So actually my papers have been quite cited by the community, looking at dark matter as Bose-Einstein condensates and so on. So we looked at how the proposal of that I just showed you would be able to search for dark matter at those frequency regimes. And basically this is the area where we think that in principle, we could do experimental searches for dark matter using our atoms in our little box. So these are just some comments. Like at the beginning, our work was very surprising because people were thinking of interferometry in space and would say, well, precisions depend in LIGO on delta L over L. So if we put your numbers there, it would be completely ridiculous. You would never see anything. And yes, indeed, you wouldn't. But we're not using interferometry in space. We're using interferometry in the frequency domain. So therefore, our precisions do not depend on delta L over L. We're using quantum resonances. So you're using a wave, as I said, that resonates with two modes. And this is actually the same principle on that Weber bars have. So Weber bars were the first instruments used to detect gravitational waves. And the idea is very similar. You have a system that has some natural modes of vibration. So they're also your phonons. And they try to detect gravitational waves by resonance of these modes with the gravitational waves. Back in the time, they cooled them down to 4 Kelvin, and they were not successful because they were too hot. Now they can cool Weber bars, and there's still work doing that at millikelvin, but still in the millikelvin regime, you are in the classical regime. So the only thing that you have is a thermal state. And with these thermal states, you can calculate that using quantum metrology, and you will find that they don't have enough sensitivity. Basically, what we proposed is a quantum version of the Weber bar. We have a Weber bar, only that we are at a system that is 10 orders of magnitude colder than the initial ones in the picokelvin regime. And in this at these scales, you are able to use entanglement and squeezing and parametric amplification and all the features of quantum metrology, which makes things much more precise. So, well, this, I'm going to skip this. We've done this in 3+1 dimensions as well. We haven't finished it. So we've done some partial studies on how would it work, because having not just, you know, one type of geometry, which is one line, could be very important. Like you could make a sphere and then it doesn't matter where the polarization of the gravitational wave is coming, or you could do different and put an array of many BECs in different, you know, configurations in order to learn more about gravitational waves. So this is a very old slide. I should update that, but this is when Virgo first did the detection. You could see how the localization and resolution of gravitational waves were still quite bad. When they added Virgo, it became, with 3 detectors, it became much better. But in principle, using a BEC, well, one BEC experiment is a few million pounds or euros or something like this. So you could, that compared to the billions of big detectors. So again, we're not competing because we work in another frequency range. But what I want to say is that a BC, you could have one in each university on Earth, and you can have many in different configurations and hopefully get better resolutions and so on. So I think I'm not going to have time to talk about the results of clocks. I'm just going to sort of advertise them. How much time do I have left, Antonio? Sorry. Probably
yeah, let's
I
say
ran out.
from 0.5. Yeah, don't worry.
Okay, so just advertising, we did some work on studying using quantum field theory in curved spacetime. This is very new, but with light to measure time. And we did this because we wanted to, say, gym exercise on how to use quantum field theory in curved spacetime, because what we really want to do is use these techniques to study atoms in the clock and be able to look at relativistic effects in that case. We've used the same sort of scheme to propose an experiment for searches of dark energy in this case, and chameleon fields. And these blue lines are the predictions of how we could extend these searches. So you could see that using these trapped instead of free falling atoms has in principle advantages. This is also our predictions of how could we extend now searches of dark energy. And like I said, we've made a patent on how to measure the local gravitational field using these effects as well. I think, did I jump something I wanted to show you here? Yeah, so this you can use also to measure the local gravitational field. So that's basically what we patent. And I'm finishing now just by saying that I hope I was able to convince you that quantum technologies are reaching scales in which we will start to be able to measure effects and some of the key predictions of quantum field theory in curved spacetime. So I think this is approaching very exciting and interesting possibilities of also from applications of your field. And the final advertisement is that I recently obtained a significant amount of funding to remake my group. So I'm going to be hiring a number of PhD students and postdocs. So if you're interested, I'm looking for people with skills in quantum field theory and curved spacetime. So please do get in touch if you feel that this line of research would be something that you could contribute to and you would be interested in doing so. So thank you, and I apologize for going over time.
No, thank you. Thank you very much for your talk. It was very enlightening, very interesting to see a new approach to all the theoretical parts we studied in experimental, real experimental outcomes. So thank you very much. That was very interesting. So we have questions. One of them is Ignacio Reyes. If you want to turn your camera and your micro and ask.
Hey.
Hi.
Hey, Ivette, thank you very much. That was a fascinating talk.
Thank you.
I have two questions. Can I raise my two hands? I mean, Mr. Speaker. Okay, I'll ask one and then you can tell me if I have time for the other one. So the first question is more technical. When you were discussing the gravitational wave detector, you started from a 3+1 problem, of course. You had these massless modes. You say we have a conformal field theory inside the BEC. There's a gravitational wave passing, but then you reduce to a 1+1 dimensional system. Now, that procedure is, as far as I know, in general, very non-trivial. Mm-hmm. You're supposed to do like dimensional reduction. Mm-hmm. You know, this is the whole story of Kaluza-Klein, right? You can have a massless theory and a higher dimensional space, but when you do dimensional reduction, the theory you get in the lower dimensional spacetime is not as simple as the one you started with. So, and in this case, it's even more confusing for me because I'm not sure, like, whether you're reducing along a direction where you have a killing vector or not. So, those steps that were not kind of explicit here, could you give?
Yes, yes, because actually, I usually always give the talk mostly to people working in quantum technologies. So I skip all that detail and I just don't talk about all those technical stuff because they won't find them interesting. And actually today I was finding like, oh, I could have added more in that direction. And I was able to use language that I usually never use. So I was enjoying just using like time-like killing vector field and things like that. I think one of the things that becomes simpler and not so problematic on doing what you're saying is that we have the BECS in a box. So we have the relativistic quantum field is trapped inside a box potential. So first, let's say, imagine that you start there with a flat space. Right, so in that case, you have no problem. People have done that many times. So now what you have is, imagine that you have a perturbation that is only coming on in one direction. So what we're doing, which is your perturbation here, right? So what we're doing there is that we're orienting that dimension to be, in this case, that's why I was saying now we're doing it with a sphere, because you would catch more interesting stuff. But in that case, you would have to align your direction with the polarization direction of your gravitational wave. Yes.
But in this case, it's true if the gravitational wave is going in one direction, but the oscillations of the metric are transverse.
Yes.
On the two directions transverse to that motion. So
yes.
How do you get rid of one of those extra directions?
Because we showed, actually, we have a very big fat paper. We have 2 papers, and it would be great because you guys would be perfect to have a look at this. There's papers that people in my other field would never have a look at. So what we did is very detailed calculations of Bogoliubov coefficients using, yes, and it is very involved, using quantum field theory in curved spacetime inside a box. And we do initially look at those other dimensions, and then we see under what circumstances they sort of become independent modes. And actually what happens with those extra, so in this case, what you're assuming is that those dimensions that are transversal are so small that you basically don't even have sort of phonons, and you're not exciting them on that direction. So if you, like, for this to work, you have to excite your phonons. If you're in the vacuum, you wouldn't see anything. So you need to excite those phonons. So what you would do experimentally, you would just excite phonons in that one direction that you're interested in, because in the other direction, you basically don't even have them in that approximation. But then we wanted to extend our analysis to 3+1. And we did do that. And we look at, the details with the time-like killing vector field and everything. And what you see in this case is in the Klein-Gordon equation, the effect of the extra dimensions. Look in your Klein-Gordon equation sort of as an effective mass term. And you can put that in. So we first did it for a massless field many years ago with Jorma Luko. You probably know him, and now from Nottingham, where we work together. And now more recently, we've done that for the phonons. So I think I'm not answering fully your question, but yeah, I don't know if you want to go into more detail or you want to discuss it with more time, but we have looked into it in detail.
Thanks. I would be happy to discuss this more later.
Yeah, if you send me an email, I could send you those papers where we have all those details.
Yeah, there is the option. We have a Slack channel where we recommend the speakers to join, because sometimes there are more questions than some minutes after the talk.
Yeah.
So if you want to join our Slack channel, then people can write you there.
Okay, I think I'm reaching this generational sort of things. Like I got into Slack some time ago, and then nobody was using it. I got out, and then okay, I'll try.
No, we have we have a lot of questions, and it's really interesting. It's not
Oh, Sylvia, thank you. Yes, I think
time.
Sylvia just sent me the link. Thanks.
Yeah, so I think we have to do that because we are a bit out of time. So thank you very much again for the talk. Hope you can progress in this field, which is very interesting for our community. And thank you, and hope to see you next time in Granada, Valencia.
Yes, I hope so. Again, thank you very much. I'm very grateful for the invitation.
Okay, thank you.
Bye.